In the first video, we explored the independence of two events. Here, we'll extend these ideas to answer what it means for more than two events to be independent. To this end, let A1, A2, up to AK be a set of k different events where k is bigger than 2. Then we can only say that this entire set of events is independent if two different properties are true. First, extending the definition of independence for two events, it must be true that the probability of the intersection of all k events is equal to the product of their individual probabilities. We can simplify this statement using some shorthand notation. On the left-hand side, we can replace the long series of intersections by the intersection of all events ai from I equals 1 to I equals k. On the right-hand side, we can replace this long product of the probability of all events by this product of the probability of events ai from I equals 1 to I equals k. This first property is called mutual independence, but alone mutual independence does not guarantee overall independence. It must also be true that the k events are pairwise independent. That is, each possible pair of events ai and aj in the bigger set must be independent. Following the definition from the first video, this simply means that the probability of the intersection of any pair of events is the product of their individual probabilities. Consider an example. At a certain ice cream shop, 40% of customers order chocolate. Contextually, it's reasonable to assume here that the customer's orders are independent. That is, one person's order has nothing to do with another person's order. Further, let A, B, and C be the events that the next three customers order chocolate, respectively. Let's utilize our assumption of independence to calculate some probabilities. First, what's the probability that the first two customers both order chocolate? That is, what's the probability that events A and B occur? Well, by our assumption that the set of events A, B, and C are independent, it follows that each pair of events in that set are independent. That is, A and B are independent. As such, the probability of A and B is the probability of A times the probability of B. Plugging in the fact that 40% of customers order chocolate, there's a 16% chance that both of the first two customers order chocolate. Next, what's the probability that all three customers order chocolate? A and B and C. By our assumption that the set of events A, B, and C are independent, it follows that A, B, and C are mutually independent. As such, the probability of A and B and C is the product of their individual probabilities. Thus, there's a 6.4% chance that the first three customers all order chocolate. Consider a final example. Suppose we flip 3 fair coins. Thus, there are 8 equally likely outcomes listed out here. Let A, B, and C be the events that coins 1, 2, and 3 are heads, respectively. That is, A is the event that coin 1 is heads, B is the event that coin 2 is heads, and C is the event that coin 3 is heads. Before doing any calculations, what does your intuition say? Do you think that the outcomes of these 3 coins, thus the events A, B, and C, are independent? Let's check your intuition. Recall that to establish independence among more than 2 events, we have to check 2 properties. First, are events A, B, and C mutually independent? That is the probability of their intersection equal to the product of their individual probabilities? Let's check. First, A and B and C, or getting heads on all 3 coin flips, can only occur one way, if we get heads, heads, heads. There is a 1 in 8, or 0.125 probability of this happening, because we see that, again, heads, heads, heads is one of the 8 equally likely outcomes in our sample space. Second, since the probability of heads on any individual coin flip is 0.5, the product of the probabilities of A and B and C, that is, getting heads on any individual coin flip, is 0.5 cubed, or 0.125. Thus, we've shown that A, B, and C are mutually independent. The probability of their intersection is equal to the product of their probabilities. Both quantities are equal to 0.125. But again, mutual independence isn't enough to say that events A, B, and C are independent. We must also check whether they're pairwise independent. That is each pair of events, A and B, the pair A and C, and the pair B and C, are these all independent? Let's check the first pair, A and B. The intersection of A and B, or getting heads on the first two coin flips, can occur two ways. If we get heads, 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 or heads and heads, but then tails on the third coin flip. Thus, there's a 2 in 8, or 0.25 probability of this happening. Second, since the probability of heads on any individual coin flip is 0.5, the product of the probabilities of A and B is 0.5 squared, or also 0.25. Thus, we've established that events A and B are independent. We can similarly establish that pair A and C is independent, since the probability of their intersection is equal to 0.25, which is also equal to the product of their probabilities, and similarly, that the pair B and C is independent. Thus, we've shown that A, B, and C are pairwise independent. Stepping back, we've shown that A, B, and C are both mutually independent and pairwise independent. Thus, in conclusion, we can say that the set of events A, B, and C are indeed independent.